So rather than throwing in the towel, let's look at some of the solutions from the past that we could consider for today. This depiction, entitled Filling Beer Casks 17th Century, has a few things that I'd like to put a spotlight on. There's aspects of the brewery architecture, the use of lifting aids, as well as the way the work is organized that makes it clear that lifting is not something that people are doing at this brewery very much at all. In the background, we see at least one lifting crane, as well as a stout beam that I think may be an additional crane, but at any rate can be used for lifting as well. We also see that the brewery is immediately adjacent to a canal, which is a lifting-free source of beer transport. But also the work has been organized such that the barrels are being washed next to the river, where the water is being collected by the crane, and the beer barrels are not even being filled inside the brewery. The beer in this photo has likely been fermented nearly all the way to completion. We see the person sort of filling the casks from a large jug outside in open air, and of course this is contrary to how we currently handle beer, where we keep finished beer far away from oxygen. I think it's likely that this is unprimed beer that they are putting in the casks to finish, likely to finish in the cellar of their destination clients. So the beer that has been processed in the brewery is probably going to be going through a series of gravity-connected vats and then dispensed into that carafe so that it can be manually transported outside into the casks. So the casks aren't even really coming into the brewery in this instance, nor are they being lifted anywhere. They're being brought out of the boat by the crane, they're being washed next to the river or canal, and then they're being filled outside the brewery. So some of the solutions to consider from this one is the architecture, the crane, and the overall handling concept that the barrels need never be lifted. Looking at another depiction from the 17th century, we see beer carriers, 17th century. Things to note here is not just the use of the lifting aid, nor the tandem lift, but also the use of the horse cart. The horse is pulling a beer sled, which is extremely low to the ground. Between the two operators is a lifting aid designed to share the load. Note that the carriers are unmatched in height, and this will likely put more load on one than another. So we see here the concepts of sliding the barrels, rolling the barrels onto the sled, and only lifting it at the last step when necessary using a lifting aid split between two carriers. I'd like to contrast how they're loading their bodies in the 17th century depiction versus how we load our bodies when we're lifting a keg today. In the old-fashioned way of things, you use lifting aids and the load is brought close to the spine. Now we do see it being unloaded unevenly left to right, but it's not hard to imagine that they might have switched shoulders between kegs to further even out the loading. Our new ergonomic approach is we tell you to lift the keg or we call you a name. I can tell you I've experienced that firsthand, as I'm certain many of the rest of you have as well. Human body mechanics are quite complicated. However, teams of experts have worked long and hard to try to simplify the complex body mechanics into something simple and approachable. They managed to take the squishy connected mess of the human body and they proved that you can simulate the compressive force in the lower back with a simple model just like this one. Now this simple model doesn't look at other forces on the body like twisting, nor does it look at left to right symmetry. Okay, so if you're lifting more with your left side than your right, this diagram will not, and this model will not consider the difference in those forces. You may notice as part of the model that there is a term for body weight force. Obviously, worker body weight isn't something we want to control. However, we can say with confidence that workers that have lower overall body weights will observe less compressive back force. That may or may not translate into better back comfort. So that same individual who has less weight in their upper body, who may be experiencing less lower back compressive force, may also have a smaller frame with which to support that force. If we think of the spine as a column in this case, they have a smaller column to support the weight that they're bearing. So it's a bit of a give and take. It's a little bit like the difference between sort of spike heels and snowshoes in terms of how they apply pressure. This is in no way intended to promote any kind of body image. However, if you are someone who does a lot of lifting, especially for work, and you do experience back pain, you may wish to consider this factor when you imagine what a healthy body weight might be for you. Because the experts were able to successfully reduce the model to a simple lever, the analysis of the loading on the back actually becomes an almost trivial math exercise for experts. The tiny red lever you see at the back there, that is the lever that represents your lower back. Because it is a small lever, your body uses a lot of force to twist your back here. All of the push down that makes the lever twist needs to be matched by your leg force pushing up. Of course, once we had the model of the body lifting, the natural thing to do is to put it to good use. So they generated what's called a back load calculator. You input the body weight, the weight load, and how far away you're lifting it from your center of mass, and it tells you the load on the body. This is an example for a 50-liter stainless steel keg and a 90-kilogram person. The resultant compressive back force, the red arrow, is 5.9 kilonewtons, or 1,300 pounds of compressive force. The yellow arrow is the force supplied by your thighs, a whopping 3.6 kilonewtons per leg, or roughly 800 pounds. It's because of the nature of the body's lever and pulley system that your body has to supply more force than the keg actually weighs. Now, this is ordinary. For a lot of loads that we lift, your muscles are contracting to a point where they're exerting much more force than the object might weigh itself. However, these are still extremely high numbers for the compressive loads on back and the support provided by the thighs. When I talked to ergonomic experts about the safe way to lift a keg, they sort of screamed and blanched when they realized exactly how heavy a full keg of beer can be, especially a rubber-bottomed one. And then when we add in the effects of slosh, it becomes a very dangerous system. On this slide, I've repeated the analysis for a 58-liter stainless steel keg with the same 90-kilogram person. The resultant compressive back force is 6.4 kilonewtons, or 1,400 pounds. The upward force per leg is 3.82 kilonewtons, or roughly 850 pounds. So that 8 extra liters of beer, which corresponds to about 20 extra pounds of beer, results in 100 pounds more compressive lower back force because of the nature of the levering system of the body. That's why the upper limit of keg weights gets to be so damaging. Here we've kept the 50-liter keg, but reduced the operator mass to 80 kilograms. The resultant reduction in body weight force corresponds to a significant reduction in the compressive back force as well as the thigh force up required. However, it is worth noting that an individual who may be lighter may also have less musculature and a different skeletal support to take the load as well. Going in the other direction, we're now looking at a 110 kilogram operator, or about 240 pounds, but keeping with the same 50-liter keg. The compressive force on the spine as well as the thigh force up is increased proportional to the person's mass and how far over they're having to lean to grab this keg. Now, it is a little bit hard to estimate, but if you have, say, a big belly, the load lever effect will actually be even higher than this because the body mass that's leveraging over your center of mass will move as you lean over. So because that load isn't necessarily tight to your body, it's having an increased lever effect on your lower back. However, this effect is a little bit hard to evaluate. It simply means that if you have a more muscular, tighter body mass rather than a slightly flabbier one, you're going to experience less lower compressive back force. Let's take a look at the stubby 30-liter keg. We've gone back to our original 90 kilogram, roughly 200 pound operator. We have the same keg diameter, but the keg is much lighter, so the loads on the body are much reduced. The same effect we saw when we had the 58-liter keg versus the 50-liter keg, but working in reverse and to our advantage. The lower back force goes down to 1,000 pounds, or 4.8 kilonewtons, and the upward force per thigh goes to about 650 pounds, down from 850, or about 2.9 kilonewtons. If we reduce the keg even further to the 20-liter corny keg, we're not only reducing the diameter of the keg, but we're also reducing its weight. So we're combining both the leverage impacts and the weight impacts to greatly reduce the compressive back force on the body by changing the levering system that the body is having to use. The loads on the body are significantly reduced in this scenario. The compressive lower back force goes down to 3.4 kilonewtons, or 764 pounds, and the upward force per thigh goes down to 2.1 kilonewtons, or 470 pounds per leg. It's worth noting that the compressive lower back force and the upward force per thigh are essentially half of what they were for the 50-liter keg and the same operator. So in order to reduce the load on our backs, because of the levering nature of the way we're lifting the kegs, we need to reduce the weight of the kegs by even more than we need to reduce the proportional compressive load on our spines. Okay? And helping in that is going to be going to a smaller diameter keg. Even if you're using a 30-liter keg, having a skinnier torpedo style is going to provide less compressive back force than the stubby style. Returning to our depiction of the 17th century beer carriers, if we make a few assumptions about the authenticity of the depiction, we can actually start doing some analyses on the compressive backload. Again, for the model we're looking at, we are not looking at the left to right asymmetric loading that this style of beer carrying presents. However, given the style, it's not uncommon to think that they might have swapped shoulders during shift to offset this asymmetric balance. Okay? The cask weighs double the amount of a keg. Because of the wood weight and because of the beer weight, it weighs approximately double what a modern keg would weigh for the same volume of liquid. We also have an additional weight of a heavy oak lifting beam, with the chain being about 15 kilograms and some estimates being made for the size of the beam and how dense oak is. Because of the way they're lifting, the load is going to be centered over their body's center of mass. This means that the lever length that affected us so heavily before when we were lifting kegs is actually going to be 0 with these individuals. This greatly reduces the impact on the lower back and on the thighs. So even though we have a package that weighs twice as much, and we're splitting it between two beer carriers, ideally, we would think that the compressive load on the back would be approximately similar to what we have today, given that they're lifting about the same amount per operator. But when we actually look at the model, we see that we get 33% of the compressive back force in the tandem lift than we do in the solo lift. And this is solely due to the fact that they are carrying it with an assistive device that allows them to center the load over their bodies. Now, using this particular assistive device requires two individuals, and that naturally has some disadvantages. But if we look at this, it's the same people carrying the same amount of beer, we've just changed how they're doing it. If we assume that the lifting beam that they used was maybe pine instead of oak, that weight drops down to 10 kilograms, and the leg force drops further still. Note that the compressive back force is hardly affected, but that's because the load is so close to the center of mass. It has no leverage, and thus the compressive back load is essentially unaffected. The 50-liter keg solo lift produces 7.6 kilonewtons of upward leg force from both legs. The tandem lift only requires 3.3. This is more than a 50% reduction. And again, this is because there is less leverage required for the load, even though the load is larger. And that depiction of the tandem beer carry was far from isolated. When you look up for historical depictions of people moving barrels, this is what you find. Not solo carries, but teamwork and lifting assists. I really appreciated this color depiction from the Metropolitan London Archives. These two individuals caught my interest because we note that, first, the front carrier looks more like a fresh-faced young person, whereas compatriot looks slightly older. You'll notice that the younger person also has less worn clothing, and the other person has a slightly battered hat. This indicates that these two individuals are probably of different age and experience in the job, meaning that we're not piling all the same age group onto these heavy lifting tasks. If we take a closer look at their uniform coats, we realize that the leather overcoat is not just a uniform, it's also more assistive devices. The padded leather shoulder is going to be there to help distribute the load and reduce the immediate friction on the shoulders that comes from the use of the lifting beam assist. When I was reviewing this material with Dr. King, she quickly pointed out that not only are the leather jackets acting as a PPE to protect the shoulder, as a sort of form of padding, they're also allowing for a pivot to happen as well. When we have the standard solo lift of the keg, we have the given keg with two different centers of mass, the keg and the lifter, separated by some distance we'll call r. In order to turn the keg, you're going to need to apply some force sideways to the keg to pivot it about your center of mass. This means that you will have to apply a twisting motion at your back. In our tandem lift, we have the heavier mass of the barrel, but because it's suspended between two people, we now have 3 centers of mass instead of 2. We're still going to call the distance between the center of the person's mass and the barrel's mass r. And we're going to assume, just for simplicity's sake, that each person weighs about the same amount. So now, in order to induce that same twist about that pivot point of the barrel itself, the force to do the twist is now going to be split between the two operators. And not only that, that force is going to be evenly applied by them because of their protective shoulder padding. So thanks to this little pivot we have, we can actually also reduce massively the twisting force involved in moving kegs around things like corners. We should find it somewhat embarrassing that the 17th century brewhouse has more mechanical lifting aids in it than many modern craft brew pubs do today. There is both a pump in the midground. In the background, it looks like someone is using a sling and hoist to lift things, probably grains, up to the top of the brewery, but we also see that there's a lot of individuals working. Now, some of those individuals are doing tasks that we assign to pumps and other types of flow assist devices. However, the nature of teamwork here cannot be missed. There are many individuals available to do the work available, and there's many types of tasks to spell people off. The sleeping individual in the foreground is often a source for some merriment when people see this depiction. People often think that they're a drunk brewery employee who is simply sleeping it off. However, a lot of brewmasters who have run small brewery operations recognize that this person is likely the brewmaster. This is mostly evidenced by their age and their manner of dress, note the apron, but it's also because at this period, the brewmaster would likely have arrived first, started things like fires, and prepared things so that his novices could then take out the tasks of brewing. Having arrived first and early in the day, he is probably taking a well-deserved nap in preparation for his more complicated work handling the yeast later on. These base ideas of ergonomics were baked into brewery design. Here we have a London, England brewery rail yard from 1870. Not only do we see the barrels being rolled, but we notice also the height of the beer train, very similar to what we saw in the Guinness barrel yard. The train is lower than the loading platform so that full barrels can be rolled down into the cars, and only empty barrels are either rolled or lifted out. So even when we put package design, lifting technique aside, and even the use of assistive devices, even the architecture of the brewery emphasizes the ergonomics that are going to be at play. This is another thing that modern breweries miss out on, partly because modern breweries are usually retrofitted into existing structures. And retrofitting breweries into existing structures makes sense for all kinds of reasons, but when we do that, we tend to do the least amount possible because of the cost involved, not necessarily fully realizing the costs that we're incurring long term. This image was originally intended to advertise the enormous size of this London Porter brewery's aging barrel from the early 1800s. However, I'd like to examine the person working in the corner in a little bit more detail. Here we can clearly see the barrels being rolled on their sides and then finally placed on their end and not stacked. This individual is likely a male, but we can see that even in the 1800s we're still rolling barrels. In another one of these advertising brag depictions that we see from this period, we know that the barrels here are full size, 164 liters likely. And note, in no case are they being stacked, in every case they are being rolled, only finally at the end being placed on their ends so that they don't roll away. And when we talk about intelligent architecture, it doesn't just stop at the loading dock. Here we see the interior at a fermentation room in a London, UK porter brewery from the late 1700s. The cellar is quite large in size. The brewer that's depicted here is going to have to transit that barrel he's moving quite far. There's tile underneath all of the fermenters, and the floor generally slopes to the center. This is important as this style of brewery is likely to have yeast overflowing onto the floor. All combined, this means that the floor is likely to be slippery. Now, moving a heavy load across a slippery surface over a long distance is normally a recipe for injury and disaster. However, we know that this facility probably operated fairly reasonably. Again, likely due to the techniques involved in handling the products, less so than the actual packages and products themselves. When the volumes of liquid to move were too small for a barrel, buckets were often used instead. Featuring a handle and often carried in a balanced tandem style again, we see that the buckets provide a relatively centralized loading, even though the heavy wood of the bucket will mean that it is a significant weight even while empty. And of course, our labor supply in the past isn't coming from just people. There is heavy use of horses and ponies and donkeys to do all kinds of labor around breweries. A lot of the depictions we see of old breweries often show the animals as well. Fun side note on this is a lot of old beer delivery depictions show a tiny little dog accompanying the delivery person. My only assumption is that this could have been a guard dog. They're often not listed as part of the brewery's staff, nor as a requirement for delivering beer, and yet they are so ever present. Many of the assistive devices we saw in previous slides were not powered by human power, sometimes not even by water power. They were often powered by equine sources, horses, ponies, donkeys, and mules. If you're used to looking at historical brewery records, you're used to seeing things that are a little incomplete. You see a lot of things that say, oh, well, the water was prepared in the typical fashion, or the barley was malted in the normal way, and there's just a lot of detail that gets left out. And you see that too with the use and descriptions of horses, or rather lack thereof. You see them in all the brewery advertisements pulling the wagons, but records on how many horses they kept and how they fed them, relatively hard to come by. Despite all that, the draft horse is a whole breed of horse specifically bred to handle the hauling of large quantities of beer in wagons and on sleighs. So this is another compounding factor. Not only do we see the use of lifting aids being quite common in a lot of the small breweries of the past, but those lifting aids are often not even being powered by people at all. And indeed, we see quite efficient uses of equine labor. Here we have a single draft horse pulling an entire canal boat. The efficiency of using the single equine engine to power that much beer is significantly more efficient than we see today. And, the solution to take from this isn't really that we should be moving beer by canal these days, but more so that you can make good, efficient use of available power, but sometimes you have to think about things a little bit differently. You can also see that the barge is almost at the same height as the riverbank next to it. This makes loading and unloading the barge relatively simple, at least at the beginning. As you unload the barge, it will float higher and higher out of the water, and thus you can then roll things off of the barge onto the shoreline.